we've considered mineral stability. Now let's talk a little bit more about pressure, temperature, time paths. These are the paths that rocks are followed in, for example, regional metamorphism, where rocks are buried deeply, and they result from crustal thickening and an input of heat during just mountain building or orogeny at convergent plate boundaries. It's not just burial. It is the pressure from being buried more deeply and orogenic heat production. And this can all take place because of burial, because of thrust faults stacking rocks on top of other rocks, thickening because of the collisional processes and the folding going on there. And inputs of heat from crustal anatexis refers to, if you have to think back a ways to remember this term, but the metamorphic processes that are dehydrating minerals, those fluids enter the rock and lower the melting temperature. That's what anatexis is. And of course, there are magmas being generated and moving through the crust, producing heat. So there's higher than normal heat flow in orogens, and it's higher than what you would expect for just greenschist amphibolite, sort of medium pressure temperature conditions. And then, of course, we're going to change those conditions too when we have uplift of these rocks and erosion of the rocks above them. It's going to change what the geotherm and what the geotherm looks like in the crust. So the facies concept, so this moving up, following a geotherm up through from lower to intermediate to higher grade metamorphic conditions, we're crossing through a series of these facies, and there's a progressive metamorphism as the rocks pass to higher grade conditions, and the mineral assemblages are constantly equilibrating to the increasing metamorphic grade. So those breakdown reactions that we just looked at, those solid-solid net transfer reactions, the dehydration reactions, the phase transformations, like with the aluminosilicate polymorphs, that's all taking place. The complete set of pressure temperature conditions that a rock experiences during this metamorphism, from burial to metamorphism and then erosion back up at the surface, that's what we're calling the pressure temperature time path. And often these pressure temperature time paths have a clockwise nature to them, because we're taking rocks that were formerly up at surface conditions or near surface conditions, and then bringing them deeper down into the crust to higher pressure and temperature conditions. And then at some point where we're collecting them is back at the surface, so they have to come back to lower pressures and temperatures. And the net result is we get this clockwise pressure temperature time path during the history of those rocks. So most examples of crustal thickening have the same kind of clockwise looping shape, whether you're considering just thickening or thrusting of large blocks of crust, or conducting heat through the rock because of magmas rising. But those paths are called clockwise pressure temperature time paths, and they're pretty normal for regional metamorphism and also for subduction zone metamorphism. So we can get at the pressure temperature time paths and to establish what pressure and temperature conditions existed in the rock several ways. We can look at overprinting of one mineral assemblage on another. So there might be a relict mineral that can tell us about part of either the prograde or the retrograde path, or both. We see evidence that a particular phase existed and that a new phase crystallized in its place, like the chlorite replacing garnet that I showed you an example of in previous slides. And we can also use geothermometers and geobarometers that allows us to calculate temperatures for the thermometers and pressures for the barometers in rocks. We can use things about the chemistry of the minerals, so the core to a rim composition. Like if we have a garnet crystallizing, it's nucleating in one spot, and it grows by adding. Here's some nucleating. Let's see, let me sketch it for you. A nucleating garnet starts in one place and then grows progressively bigger. And the chemistry at the core of the garnet could be quite different than the chemistry at the rim. Let's say the chemistry at the core is more calcium rich than the rim, which was more iron rich. That's going to tell us something about the PT conditions as they changed during the metamorphism in that rock. That's one way we can do it. There are experiments that have been done to look at elemental exchange reactions. And this diagram is showing us, I just want to use this as an example, this garnet and biotite reactions. And what that's doing is looking at the ratio of iron and magnesium in the garnet and the biotite that's in the rock. And if you assume, for example, that all the iron and magnesium in a rock is contained within the biotite and the garnet, that's actually a temperature-controlled process as to how much iron goes into the biotite and how much iron goes into the garnet, how much magnesium goes in the biotite, how much magnesium goes into the garnet. And they share the iron and magnesium in that rock. Well, it's temperature-controlled, so what that allows us to do is to take all these different experiments that have been done by these different authors and to plug in the actual elemental ratio that we have for iron and magnesium in garnet and in biotite and calculate temperatures. And we use their equations. They plot on these steep lines like this. And depending on their experiments, that temperature range that you get is going to vary. And so what this diagram is showing you is that between all these different authors, we're seeing a temperature range that falls somewhere between 400 and 550 degrees Celsius for this example. And we can use other measures, and this is a garnet aluminosilicate quartz and plagioclase barometer that are represented by these blue lines. I won't go into that, but the idea is that you can use some of this experimental evidence to calculate pressure and temperature conditions for your rock and to narrow down that range to be pretty specific. So in this case, the rock had to have been metamorphosed between 400 and 550 degrees Celsius and between about 0.2 and 0.6 gigapascals, which that corresponds to intermediate depths in the crust, so the middle parts of normal crust. We can combine those thermobarometers with mineral chemistries, and this is showing you an example garnet, and all of these points on this garnet can be analyzed, and from rim to rim you can see that the chemistry changes within a garnet. So here we have the almandine component of the garnet, so that's just looking at the iron component. We have pyrote plotted here, which is magnesium, spessartine, which is the manganese, grossular, which is the calcium. And we see that the rims of the garnet are very iron and magnesium rich out here. And the core is much more manganese and calcium rich. We can use the iron and magnesium in the core and the rim and compare it to the distribution of iron and magnesium in coexisting biotite and calculate different temperatures for the growth of the core of the garnet than temperatures that we might get for the growth of the rim of the garnet. And then that would allow us to plot on a pressure temperature diagram, estimate core conditions, so 600 degrees and almost 0.9 GPa, versus rim conditions, again close to 600 degrees but much lower pressure, so 0.5 GPa. And that allows us to establish a pressure temperature path. I should say you can add the element of time to that pressure temperature path by doing some geochronology or thermochronology. Now, you can go one step beyond those phase diagrams and that thermobarometry and do something that is thermodynamic modeling of rocks. And what you need to do that is to get the whole rock chemistry of your rock. And that requires crushing it and having it analyzed by something like an X-ray fluorescence machine that gives you the percent of each element in that rock. And you can work out which oxides are present. So in this case, in this example, I've got sodium, calcium, potassium, iron, magnesium, aluminum, silica, water, and titanium all considered. Manganese not there because it's often a very small component of a rock. But there are programs that are called, one is called Thermocalc, one is called Perplex, or Purple X it looks like. And you can input your whole rock chemistry information and actually model a phase diagram just for your rock. So it gets very specific, and you can narrow down the pressure and temperature conditions for metamorphism and the PTT path very well. And I've done this. This is for a pelitic rock from the Himalayas. It's from a granitic gneiss-dome, and this is the host rock to those granites. And we plugged in those components and looked at this rock in thin section and did the modeling with the thermodynamic modeling program, and I used Perplex for this one. And what we found was the stability for peak conditions was somewhere about 650 degrees Celsius and about 0.75 GPa. But we also saw a stable mineral assemblage in this rock that existed at lower pressure and temperature conditions, so on the retrograde path when these rocks were exhumed. And the retrograde metamorphism was between 600 and 650 degrees Celsius and closer to 0.5 GPa. So what you'll notice is the high pressure, higher grade or peak conditions, kyanite was stable. There's kyanite right in there, abbreviated KY. And the retrograde conditions, sillimanite was stable. So they weren't growing at the same time. Kyanite was growing at near peak conditions, and sillimanite was actually on the retrograde path. So the whole pressure temperature conditions changed. Something else you'll see is where garnet is stable. I just highlighted in this line right here in red. To the right of that line, at higher temperatures and higher pressures, you see garnet in each of these fields. So those are the conditions where garnet is actually stable in this rock. And it's not a smooth curve where you have garnet on one side. and biotite and quartz on the other side, plus maybe a pelage to grow garnet. So we don't see a nice smooth curve, but we are seeing the mineral reactions. They're cobbled together. So that field, we have biotite, white mica, starlite, plagioclase, rutile, and ilmenite. And then something is breaking down, because on the other side of this garnet stability line, we see biotite, white mica, starlite, plagioclase, garnet, and rutile. So we've broken down some of the iron and magnesium and aluminum in the minerals at lower grade conditions to grow garnet at higher pressures. We'll also see on here in the blue line is the kyanite-sillimanite phase boundary. So to the right, at higher temperatures, at the higher temperature side of that blue line, we see sillimanite stable. At lower temperatures, we see kyanite stable, also at high pressure conditions. So all this together, what I hope you've learned in the discussion of metamorphism, mineral reactions, and thermobarometry and PT-PAS are that mineral stability in metapelites and mafic rocks really depends on the chemical components in the rock. And that establishing what those minerals, what the stable minerals should be, is pretty complex. And when we're looking at phase diagrams, they're very simplified. The pressure, temperature, time paths follow a clockwise loop through pressure and temperature space. And we can get at that PT path by looking at overprinting relationships, which minerals are replacing other minerals, looking at elemental zoning within minerals like garnet, or doing thermobarometry to calculate PT conditions for metamorphism in those rocks. And the thermobarometry, we can do that by conventional thermobarometry, like the iron and magnesium exchange between garnet and biotite. Or we can do what's called an isochemical phase diagram. So a phase diagram generated for a specific rock, and using the whole rock chemistry and using one of the thermodynamic modeling programs.